Welcome to 6th Science Conclave Physics Lab. Introduction to Fiber Optics.
Fiber uses light-based optical technology. Light travels along a fiber optic cable in the form of photons. Since fiber relies on beams of light, it's less susceptible to noise and interference than other data transfer mediums such as copper wires or telephone lines. Unlike wires and lines that have limited capacity, fiber optics are capable of transmitting billions of digital bits per second.
Total internal reflection.
Recall that any time light strikes a surface, it can either be absorbed by the material, reflected from it, or pass into and through it. The latter we call refraction. It's easier to see from a top view. Reflection and refraction can happen at the same time, but if a light ray hits the surface at an angle greater than the critical angle, it will be completely reflected and not refracted. To create this same effect in an optical fiber, engineers create a core of glass, usually pure silicon dioxide, and an outside layer called cladding, which they also typically make from silicon dioxide, but with bits of boron or germanium to decrease its index of refraction. A 1% difference is enough to make a fiber work.
Intrusion detection.
Long perimeters with accurate intrusion location. A single processor with a single standard fiber cable can protect long perimeters. The same setup can be used to protect mixed environments, such as welded mesh, chain link fence, top walls, and buried applications. The fiber is static. The display shows no spikes. An intrusion would shake a section of the fiber, and a spike would show due to the change in the nature of the backscattered energy.
Archimedes' principle. Archimedes' principle states that the force of upthrust exerted by a liquid on a body is equal to the weight of liquid displaced by the body when it is immersed in liquid. This principle can be demonstrated as follows. Weigh a stone in the air using the spring balance. Take a glass beaker filled with water exactly up to its spout. Place another beaker alongside to collect water flowing out of spout. Immerse the stone completely in water while holding the balance in hand. The water will start flowing out of the spout into the smaller beaker as soon as the stone is immersed in water. It will be observed that the weight of stone decreases. This is a result of upthrust exerted by water on the stone. Now weigh the displaced water along with the beaker. Then weigh the empty beaker. The difference between the two weights is equal to the loss in weight of stone in the water. Conservation of energy.
Do you know energy cannot be created or destroyed? It can only be stored or transferred. All energy in this world exists in two forms. One is called potential energy and the other is called kinetic energy. Remember, potential energy is stored energy in the object, whereas kinetic energy is energy of motion. Look at this big rock on the slope. If it falls down, it can do a lot of damage. It has a lot of potential energy, which means a lot of stored energy. See this? The stone is falling down. Now it has kinetic energy. The potential energy has changed into kinetic energy.
Bernoulli's principle.
Bernoulli's theorem and its applications. Daniel Bernoulli, a Swiss mathematician and physicist, stated a theorem which gives the interaction between the pressure acting at a point on the surface of the liquid and the velocity of its particles. Bernoulli's theorem states that the total energy of a small amount of an incompressible liquid flowing from one point to another remains constant throughout the displacement.
Bernoulli's principle states that a stream of faster-moving fluid has lower pressure than the slower-moving fluid around it. As the fluid speeds up, particles spread out, resulting in fewer collisions and less pressure. With the balloons originally hung approximately 5 inches apart, when you blow the low-pressure, high-speed stream of air into the higher-pressure atmosphere, it causes the balloons to constrict into the low-pressure region.
Air track experiment.
Connected to blow air through here, and timing gate here, and bounces on the rubber band there, and off it goes back up the track.
Fiber optic transceiver.
Transmitter. A network device that converts an incoming electrical signal into a modulated optical signal for transmission down an optical fiber link. Receiver. A network device that converts an incoming modulated optical signal into an electrical signal for transmission down an electrical communication circuit.
Standing waves. Satellite communication.
A satellite is an artificial body placed in an orbit around the Earth or another planet. The communication satellites relay around the world telephone and fax messages, television programs, radio signals, and so on. Principle of satellite communication. The process of communication begins at an Earth station. The Earth station is an installation designed to transmit and receive signals from a satellite in orbit around the Earth. Earth stations send information in the form of high-powered, high-frequency signals to satellites that receive and retransmit the signals back to Earth. These retransmitted signals are then received by other Earth stations in the coverage area of the satellite. The area which receives the signal from the satellite is known as the satellite's footprint. The transmission system from the Earth station to the satellite is called the uplink, and the transmission system from the satellite to the Earth station is called the downlink. Here you have the schematic representation of the principle of satellite communication. To avoid confusion, the uplink and downlink frequencies are kept different. Before designing a satellite communication system, we must choose the orbit in which the satellite is to be placed. Orbits are of three types, namely geostationary orbit or geosynchronous orbit, polar circular orbit, and inclined highly elliptical orbit. Geostationary or geosynchronous orbit. In this type of orbit, the satellite takes 24 hours to circle once around the Earth. Since the period of revolution of the satellite is equal to the period of rotation of the Earth, the satellite appears to be stationary in the sky. For this reason, this 35,900 kilometers high equatorial orbit is called a geostationary orbit. The geostationary orbit is also known as Clarke's orbit. This is in honor of Arthur C. Clarke, the man who first suggested in 1945 that satellites in geosynchronous orbits could be used for communication purposes. Entire Earth can be linked or covered by the communication network if three geostationary satellites are placed at the vertices of an equilateral triangle. Each of the satellites covers 1/3 of the globe. Polar circular orbit. This type of orbit is placed 1,000 kilometers above the Earth's surface. It passes over the poles. The angle of inclination of this orbit is 90 degrees. It scans the whole Earth in every 12 hours. Satellites used for weather monitoring are launched into a polar orbit. Inclined highly elliptical orbit. It is used for establishing communication with regions at high latitudes. The angle of inclination is equal to 63 degrees.
Newton's rings. The phenomenon of Newton's rings, named after Isaac Newton, is an interference pattern caused by the reflection of light between two surfaces, a spherical surface and an adjacent flat surface. When a parallel beam of monochromatic light is incident normally on a combination of a planar convex lens and a glass plate, a part of each incident ray is reflected from the lower surface of the lens, and a part, after refraction through the air film between the lens and the plate, is reflected back from the plane surface. These two reflected rays are coherent. Hence, they will interfere and produce a system of alternate dark and bright rings. Apparatus: monochromatic light, wooden mount. This is a rectangular shaped box at the bottom of which we place plain glass material and the lens. Light is directed to the lens through this reflector. Optically flat glass plate. A planar convex lens. Traveling microscope. Procedure: turn on the sodium lamp. Place a planar convex lens on the plain glass plate with curved surface in contact with the glass plate, and place this system inside a mount placed under a traveling microscope. The reflector on the mount will direct light onto the optical system. Focus the traveling microscope to see the bright and dark circular fringes. Fix the vertical crosswire of the microscope on the 20th bright ring at leftmost end and record the reading on the horizontal scale. Repeat these measurements for microscope movement from left to right and evaluate the diameters of different rings.
AC/Wheatstone Bridge.
Wheatstone Bridge. A Wheatstone bridge is an arrangement for measurement of unknown resistance. A Wheatstone bridge consists of 4 resistors of resistances P, Q, R and S connected together to form a quadrilateral or bridge ABCD. The pair of opposite junctions B and D is connected through a galvanometer, and the other pair of opposite junctions A and C is connected through a battery and a key. If resistances of 3 of the resistors in the bridge are known, then the bridge can be used to calculate the resistance of the 4th resistor. Let us see how a Wheatstone's bridge is used to calculate the resistance. First, we will have to balance the bridge. The value of the resistors P, Q, R and S are so adjusted that the galvanometer shows no deflection on closing the key. This means that no current is flowing in arm BD, and therefore the potential at B is equal to the potential at D. Now the bridge is said to be balanced. P by Q is equal to R by S. Knowing the values of 3 resistors P, Q and R, the unknown resistance S can be found out.
Diffraction grating.
Diffraction of light. A ray of light bends slightly as it passes around the edge of an object. The phenomenon of bending of light from its straight line path around the corners of an obstacle or slit is known as diffraction. Diffracted light can produce fringes of light, dark or colored bands. We observe that the process of diffraction becomes much pronounced when the dimensions of the slit are comparable to the wavelength of light.
The slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the 2 tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing.
Dispersion.
Dispersion of white light. What happens when a beam of white light strikes a prism? When a narrow beam of ordinary white light is passed through a glass prism, different wavelengths travel through the glass at different frequencies and appear as a continuous broadband of different colors called the spectrum. This phenomenon by which a ray of light splits into its constituent colors when it is passed through a transparent medium is known as dispersion. Find out more facts about the spectrum yourself.
Eddy current tube.
What is eddy current? The word eddy literally means a circular current. This experiment shows that when a conductor is kept in a changing magnetic field, currents are induced in the body of the conductor. These are currents that occur in very small loops and are called eddy currents. The magnitude of eddy currents is given by I is equal to -1 by R into d phi b by dt. The direction of eddy currents is given by the Lenz's law or Fleming's right-hand rule. Lenz's law states that the direction of induced current is such as to oppose the very cause producing it.
Again, we see the magnet dropping through the tube. The red lines are added to represent the magnetic field produced by the magnet. As the magnet falls, the magnetic field in the copper tube changes. This variation in the magnetic field induces an electric current, as predicted by Faraday's law. Faraday's law states that any change in the magnetic environment of the copper tube will cause a voltage to be induced in the tubing. This induced voltage creates electric currents in the copper called eddy currents. They're called eddy currents due to the circular motion they undergo. All electrical currents produce their own magnetic fields, which are illustrated in this diagram by green lines. Another law predicts the direction these induced electric currents and their magnetic fields will flow. This is called Lenz's law. Lenz's law states that when an electromagnetic field is generated by a change in magnetic flux, according to Faraday's law, the polarity of the induced electromagnetic field is such that it produces a current whose magnetic field opposes the change which produces.
Magnetic field lines.
Magnetic field. Magnetic field is a region near a magnetized body where magnetic forces can be detected. Let us understand the concept of magnetic field with the help of an activity. Place the cardboard over a magnet. Sprinkle some iron filings on the cardboard. Tap the cardboard gently. We observe that the iron filings align themselves in definite patterns. These patterns indicate the magnetic field of the magnet. A magnetic field is represented graphically by lines of force. Patterns of lines of force. Patterns due to two bar magnets placed with opposite poles facing each other. Patterns due to two bar magnets placed with like poles facing each other. Properties of magnetic lines of force. Let us now summarize the properties of lines of force. They are closed and continuous curves. Outside the magnet, the lines of force are directed from the North Pole towards the South Pole of the magnet, whereas within the magnet, the magnetic lines are directed from the South Pole towards the North Pole. Lines of force repel each other. Lines of force never intersect.
The scientist who invented the homopolar motor is named Michael Faraday in the 1820s. What you will need to make a homopolar motor is AA battery, copper wire, pliers, and neodymium magnet. I made 3 different shapes with the copper wire, and this is a basic setup. I made a heart, a spiral, and a square. The first thing I'm going to do is put my neodymium magnet on the bottom of my battery. And then I'll take my simple shape and put it on. And it starts to spin. Now I'll show you my spiral. The next thing I'll show you is the heart I made out of the copper wire. So the electricity flows from the battery and through the copper wire. When electricity flows through the copper wire, it creates a magnetic field. When this magnetic field connects to the magnet, the force between the two propels the wire to spin.
The direction of motion is given by Fleming's left-hand rule. Fleming's left-hand rule. Extend the thumb, forefinger, and the middle finger on the left hand in such a way that all the 3 are mutually perpendicular to each other. If the forefinger points in the direction of the magnetic field, the middle finger in the direction of the current, then the thumb points in the direction of the force exerted on the conductor.
Focal length of convex lens.
Principle of UV method. The focal length of a convex lens is calculated using the lens formula. 1 by f is equal to 1 by v minus 1 by u is the lens formula. where u is the distance between the object and the lens, v is the distance between the image and the lens, and f is the focal length of the lens. This lens formula is applicable to both convex and concave lenses. The lens formula for the convex lens after applying appropriate sign convention is f is equal to uv by u plus v. Arrange a candle, a screen and the convex lens as shown here. Adjust the position of the lens so that a blurred image of the candle is obtained on the screen. Now move the screen back and forth till a sharp image is formed on the screen. Measure and record the distance between the lens and the object, and also the distance between the screen and the lens. Repeat the experiment by changing the position of the lens and then the screen until a sharp, well-defined image of the candle is formed on the screen. The focal length is determined by using the lens formula. The average of the focal length is calculated.
Ultrasonic distance meter.
Determination of the depth of an ocean by echo sounding. The depth of an ocean is determined with the help of sonar by echo sounding. Sonar stands for Sound Navigation and Ranging. Sonar is a system for detection of underwater objects by reflected or emitted sound to aid the piloting of ships. Sonar uses ultrasonic waves to detect and locate objects underwater. Ultrasonic waves produced from the transmitter kept in a ship are directed towards the ocean floor. The ocean floor reflects these waves. By measuring the time interval t between the generation of the waves and reception of the echo, we calculate the depth of the ocean by using the relation d is equal to v into t by 2, where v is the velocity of ultrasonic waves and d is the depth of the ocean.
Over here, we're over a little mini trench, and the boat takes 2 seconds. Over here's a seamount, and the boat takes 1 second, so it's half a second. Over here, we're over a big trench. Takes longer.
Solar cell.
Every hour the sun's energy falls on the planet is equal to the amount of energy used by the entire human population in 1 year. The energy from the sun is in limitless supply. Unlike oil or gas, solar power is a reliable source of energy whose prices never fluctuate. Solar energy is free. How does it work? Solar electricity is generated using photovoltaic cell technology that has been optimized over years of research. Simply put, the greater the intensity of the sun, the greater the current of electricity. Solar panels collect sunlight and turn it into direct current or DC electricity. Even on cloudy days, your panels will absorb sunlight. The system's inverter then turns this DC electricity into the same electric current that comes from your traditional utility lines.
Working principle.
Sunlight is made up of tiny packets of energy called photons. Every minute, enough of this energy reaches the Earth to meet the world's energy demand for a whole year. Photovoltaic panels consist of many solar cells. These are made of materials like silicon, one of the most common elements on Earth. The individual cell is designed with a positive and a negative layer to create an electric field, just like in a battery. As photons are absorbed in the cell, their energy causes electrons to become free. The electrons move toward the bottom of the cell and exit through the connecting wire. This flow of electrons is what we call electricity. By combining solar cells and photovoltaic panels, we can produce just the right amount of electricity to perform a specific job, no matter how large or small.
Thank you.